All right, these are the slides on roller coasters and how energy is affected by roller coasters. All right, so just to review, energy is the capacity to do work. All forms of energy are scalar, which means it is only magnitude, no direction. And the unit for all forms of energy is the Newton meter or the joule. Now, the four basic ways of storing energy are potential energy, kinetic energy, internal energy, rest mass. We're just going to be focusing on potential and the kinetic energy. So we learned about the law of conservation of energy, which states that energy cannot be created or destroyed. It can be transferred from one place to another, but it can also change and transform into other forms of energy. So we learned about mechanical energy. Now, mechanical energy is the energy due to the position of something or the movement of something. And so kinetic energy is the energy due to the movement of something. And the potential energy, there are two forms of potential mechanical energy. There's gravitational potential energy and elastic potential energy. So mechanical energy is conserved, right? So in an isolated system, if there's no losses or friction, then we'd say that the total mechanical energy in the system is conserved. They transform in between those three forms of energy, but the total amount of mechanical energy remains the same. So let's answer this question. Why is the tallest point on a roller coaster that initial drop? So in order to answer this, we did a roller coaster simulation. So what we do is the first one we did was we set up the simulation just like that, and then we as explain what happens to mechanical energy, kinetic energy, gravitational potential energy as it goes up and down. Well, the mechanical energy remains the same, but what's happening is as it's going down, that gravitational potential energy is transforming into kinetic energy. As it's going up, the kinetic energy is transforming back into gravitational potential energy. So then the next thing we did was we set it up where that initial drop is taller than that hill in the middle, and it was able to make it over. Well, now if we made the hill taller than that initial drop, it won't be able to make it over. Uh, Now, and that's because of it does not have enough gravitational potential energy, right? So that initial drop has to be that tallest point because if you transform all that mechanical energy back into gravitational potential energy, well, potential energy is at a height, and if you turn it all, you're at that maximum height. So it can only go up in a perfect world, no losses to the outside world. It can only go it can only go as high as that initial drop. All right. So then we set this simulation. This is just to show how forces interact or how you feel on a roller coaster, like where you're going to feel the heaviest, where you're going to feel lightest, where you're going to feel weightless. Now the next one was we turned on the thermal or the like we drag. So that means we're losing energy to the outside world. So we're not destroying it, but what you would notice is that that mechanical energy slowly goes down because you're losing some of that energy to the outside world. So the answer is explain why the tallest point on a roller coaster is that initial drop, and it's because well, that's where it's going to have the most gravitational potential energy, and that's where it's at the highest point, right? If you cannot create more energy to be at a taller point. And when is the car moving the fastest on the roller coaster? How is this known? It's going to be at the bottom because that's where the most amount of gravitational potential energy has been transformed into kinetic energy. So we'll answer this question. Why is the fastest point on the roller coaster the lowest point? So if we look at this, we'll notice this little graphic. The total amount of mechanical energy does not change. It stays at 100. Now, when it's in motion, it has kinetic energy. And energy cannot be created or destroyed. So the mechanical energy doesn't change, but notice that it's going the fastest at the lowest point. That's where it has the most kinetic energy. So it's going the slowest when it's up higher because that's when it has the most amount of gravitational potential energy, least amount of kinetic energy. So the reason why no point can be taller than an initial point is because you don't have enough mechanical energy. If you transformed all that mechanical energy into gravitational potential energy, there wouldn't be enough to be at a taller point than that initial drop if they started at rest. So let's take a look at this. At what point on the track is the car going the fastest? Well, I can look at this and say it's going to be C because it's at the lowest point. That's when the most amount of gravitational potential energy has been transformed into kinetic energy. At what point along the track is it going the slowest? It's going to be A. That's the tallest point, right? So it has more gravitational potential energy, least amount of kinetic energy. So rank the points along the track the cars will be going fastest to slowest. So all I do is I have to start at the bottom and go up. So I know it's going to be C, then E, then D, then B, then F, then A, because the lower you are, the more kinetic energy you have, so the faster you're going. And without any external forces, will the cart ever be able to go higher than point A? Answer is no. So if it starts at rest, it won't be able to go taller than that point because even if you convert all that mechanical energy into gravitational potential energy, it can only be at that point. All right, so does mass affect the speed of the carts on a roller coaster? So let's take a look at one problem here, and we'll just do the math behind this problem. So a marble has a mass of 5 kilograms and starts at rest and rolls down the track, hitting the spring with a spring constant of 10 newtons per meter. The heights of the poles are HA is 20 meters, HB is 15 meters, HC is 5 meters, HD is on the ground, HE is the same height of HB, HF is at 6 meters. Fill out the table below for all the points along the track. Then answer how far back the spring is compressed at point F when the marble comes to rest. Use 10 meters per second squared for G. Fill out the chart below for the mechanical energy of the different points along the track. All right, a lot to take in here, but let's just take this one step at a time. So let's look at point A. Well, I know it's at rest, so it has no kinetic energy. Well, I can calculate that gravitational potential energy. It's going to be the mass, which is 5, times gravity, which is 10, times the height, which is 20, and I get, well, it's going to be 1,000 joules of gravitational potential energy. Well, now I can find the total amount of mechanical energy by adding those 3 types of mechanical energy together, and I'm going to get 1,000 joules of total mechanical energy. Now, notice what happened when I filled that out. The mechanical energy is not going to change. Now, what types of mechanical energy, those will change, but notice that I'm always going to have 1,000 joules of mechanical energy. And it's not just these 6 points, it's every single point along this track. So now I can look at B. So I know at point B it's going to be moving. Well, then all I have to do is, I can't calculate it though. I cannot calculate the kinetic energy yet because I do not know the velocity. However, I can calculate the gravitational potential energy. So the mass is 5, gravity is still 10, and the height is 15, and I get 750 joules of gravitational potential energy. Now notice what happened. I know the rest of that mechanical energy is going to be kinetic energy, 250 joules. And the reason why is because all 3 of those have to add up to 1,000 joules. Also notice what has happened. Point B and point E, I filled them out with the exact same thing. And that's because they're at the same height. So they're going to have the same gravitational potential energy, same kinetic energy. So I can do that for C, D, and F. Right. So now what I can do is, now that I know the kinetic energy, I know the mass, I can calculate how fast the marble is going. So I can just plug it into my equation for kinetic energy and solve for V, and that's what I get, right? So it's kind of hard to see there, but it's like 0, 10, I think 17.3, 20 meters per second, 10 meters per second, and then 0, right? Because it comes to rest on the spring. Then you can calculate how far back the spring is compressed. I'm not really concerned about that right now, but now let's look at another problem. Except this time, I'm doing the exact same problem, except now notice the mass is different. So now I'm rolling a 20 kilogram marble down this track. Well, I plug in everything that I know at first. It starts at rest. Now I can calculate the gravitational potential energy. Notice that the gravitational potential energy is a lot more than the last one because it has a larger mass, right? Same height, same gravity, larger mass though, so it has more gravitational potential energy. So I add all those up and I get my mechanical energy. And notice it's the same thing for the entire track. So I can do the same thing that I did on that last problem. Calculate the gravitational potential energy. The rest has to be kinetic energy. B and E are the same, and I can do that for the rest of them. But now I can solve for the velocities, and I plug everything in. And notice what happens though. Notice the velocities are the same. Now, that spring, it's going to be pushed back farther because I have a larger mass. Well, there's more, gravitational potential energy, more kinetic energy, but notice the velocity did not change. I just changed the mass in these 2 problems, and the velocity did not change. So let's take a look at this, right? Let's take a look at this graphic again. So what happens to the total mechanical energy of the cart as it goes up and down the track? Well, notice the total amount of mechanical energy does not change. It remains at 100. So I could set up an equation and say, just set up 4 arbitrary points or infinite amount. It doesn't matter. And I know the mechanical energy at all of those points are going to be equal. And that's what I did at that first equation. Now what I can do is I can expand it out and say, well, okay, the mechanical energy is the kinetic energy plus gravitational energy plus the elastic potential energy. I don't have any elastic potential energy in this, right? So we know that we cannot create or destroy energy. No elastic potential energy. So it's 0 throughout this entire track, unless, the cart gets stretched or it transfers it into a spring or whatever, but it doesn't do that on this roller coaster. So look at what happens when I do that. I set the mechanical energy equal at every point, and if the elastic potential energy is 0, notice mass is in every single term in this. It doesn't matter. I'm going to set mechanical energy equal at every single point. Mass will be equal at, or mass will be, sorry, the mass will be in every single term at every single point. So the mechanical energy of the cart does not change as the cart moves along the track. Now, because the cart doesn't have any elastic potential energy, the cart's mass will cancel out in every term. So the velocity of the roller coaster is mass independent. It doesn't matter, just like we saw in those equations that we did, that, yeah, it affected the amount of gravitational potential, the amount of kinetic energy, but it did not affect that velocity. And it's because the mass is in both kinetic energy and gravitational potential energy. And that's what the mechanical energy is transforming into on a roller coaster. So once again, there is too much unknown in the universe to take a break from learning. Get out there and question everything.